Hi, my name is Isa Nadira, and today I will be presenting on zero-dimensional nanomaterial. This presentation was prepared by myself and my partner Noor Hidayah Kasim. Our presentation will cover the following points. The first one is introduction, types of zero-D synthesis method, advantages and disadvantages, application, and the last one is future challenge. For the interactions, zero-D materials or zero-dimensional nanomaterials are materials where all three dimensions are confined to the nanoscale, typically less than 100 nanometers. This means that they have no dimension larger than this, and they exhibit unique physical and chemical properties due to their size and high surface area to volume ratio. For example, quantum dots, fluorines, and nanoparticles. There are three main types of zero-D. The first one is quantum dots. These are semiconductor particles that exhibit quantum mechanical properties. Their electronic and optical properties can be tuned by changing their size. This tunability makes them useful in various applications like displays, solar cells, and biological imaging. The second one is fullerenes. These molecules are composed entirely of carbon and can take the form of a hollow sphere, ellipsoid, or tube. Fullerenes have application in material science, electronics, and nanomedicine. Their unique structure allows for various functionalities, including drug delivery and as superconductors. The third one is nanoparticles. These are particles of various materials such as metals, ceramics, and polymers at the nanoscales. They are used in catalysis to speed up the chemical reactions in medical imaging and to enhance contrast in drug delivery to target specific cells and as building blocks for other nanostructures. Each type of zero-D nanomaterial has distinct properties and a range of applications, demonstrating the versatility of nanotechnology. Zero-D nanomaterial can be synthesized using both bottom-up approach and top-down approach. Chemical vapor deposition (CVD). This method is used to synthesize quantum dots and other nanoparticles. It involves depositing vaporized precursor onto a substrate where they react and form nanomaterials. This technique allows for precise control over the size and composition of the nanoparticles. Solid process. This process involves transitioning a system from a liquid solid into a solid gel phase to form nanoparticles. It is commonly used to produce the oxide materials and allows for the synthesis of material with high purity and uniform particle size. Colloidal synthesis. This method produced nanoparticles by mixing precursor solution and allowing them to react and form nanoscale particles. It is widely used for producing the metal and semiconductors nanoparticles, offering a control over the size and shape. For top-down approach, mechanical milling, this technique reduces bulk materials to the nanoscale through mechanical forces such as grinding or milling. It is a simple and cost-effective method, but can result in a broad size distribution of particles. Lithography. This process is used in semiconductor fabrication to create nanoscale patterns. It involves patterning a surface using light or electron and then etching away the exposed area to form nanostructures. Lithography is essential for producing integrated circuits and other nanoscale devices. Each synthesis method has its advantages and limitations, and the choice of method depends on the desired properties and application of the zero-D nanomaterials.
Now, let's move on to the advantages and disadvantages of zero dimension nanomaterials. First, let us take a look at the advantages. So, the first one is unique optical properties. Quantum dots can emit light of specific wavelengths when excited, making them valuable in display technologies, imaging, and sensors. The second one is high surface area. The large surface area to volume ratio enhances catalytic activity and makes them suitable for applications like drug delivery and chemical sensors. The third one is quantum confinement effects. These effects lead to discrete energy levels and novel electronic properties, which can be exploited in transistors, lasers, and other electronic devices. The fourth one is enhanced reactivity. Their small size and high surface energy make them highly reactive, which is beneficial for catalytic and chemical processes. And the last of its advantages is versatility. They can be synthesized from various materials such as metals, semiconductors, polymers, and it also can be tailored for specific applications. And the opposite to advantages, well, of course, the disadvantages of zero dimension nanomaterials. The first one is synthesis complexity. Producing zero dimension nanomaterials with a uniform size and properties can be challenging and quite expensive. The second one is stability issues. They can be chemically or thermally unstable, leading to aggregation or degradation over time. The third one is toxicity concerns. Some zero dimension nanomaterials, especially those used in medical applications, may pose health risks due to their high reactivity and potential to generate reactive oxygen species. The fourth one is limited scalability. Scaling up the production processes while maintaining quality and consistency is often difficult. And last but not least is complex characterization. Analyzing and characterizing these materials require advanced techniques and equipment, which can be resource intensive. There are various applications of the zero dimension nanomaterials, such as in the electronics, quantum dots are used in QLED displays, offering high brightness and color purity. Also, the nanoparticles enhance the performance of batteries and supercapacitors by improving conductivity and energy density. While in the medicine, nanoparticles are used for targeted drug delivery, improving the efficacy and reducing side effects of treatments. The quantum dots and other nanoparticles are used in diagnostic imaging and as contrast agents. The application of zero dimension nanomaterials of the energy is that the nanoparticles improve the efficiency of solar cells and catalyze the reactions in fuel cells. Quantum dots can be used in light emitting devices for energy efficient lighting. For environment, nanomaterials are employed in water purification and air filtration systems to remove contaminants. And the last one, it acts as a catalyst as high surface area nanoparticles serves as a catalyst in chemical reactions, enhancing reaction rates and selectivity. While the zero-dimension nanomaterials spread like wildfire in the development of the industry, these are the future challenges that should be taken into measure. Before I end our presentation, my name is Nurhida Kasim, together with my partner, Che Iza Nadira Che Shabuddin. Both of us would like to thank you for sparing us your precious time to listen to us. Thank you very much and have a good day.